Okay, welcome everybody. This is George Wright with M2 Technologies. We're a manufacturing and technology and process consulting firm, and where we do have the benefit of providing the Autodesk manufacturing solutions to the industry. Today, we're going to dig deeper into the value of the collections by showcasing HSM as a CAM solution. At this time, I'm just going to turn it over to Wayne from Autodesk, who's going to lead us through the demonstration. Wayne, please give yourself an introduction and take it away.
Very cool. Thank you, George. Good morning and afternoon, everybody. Thanks, George and Kristen and the team at M2 Technologies for having me on today. So my name is Wayne Griffenberg. I'm part of Autodesk's design and manufacturing team. I'm a technical specialist on that team. I have over 20 years experience in manufacturing, particularly in the CAD/CAM aspects of design and manufacturing. So today, is another edition, if you will, a webinar of the series that was started by M2 Technologies last fall, where we're bringing you a background and more broad scope of an overview of what's available in manufacturing at Autodesk. And today is going to be a deeper dive into that series of webinars. Our topic today, as George had mentioned, we're going to be talking about our HSM, which stands for high-speed machining, which is a product that is embedded, or shall I say integrated, into Autodesk CAD technologies. And so we're going to do a deeper dive on what that means. What is integration? And then we're going to go into more of a deeper dive into milling toolpaths, adaptive clearing, which is our high-speed and high-efficiency roughing solution, to talk a little bit about turning toolpaths and multi-axis toolpaths. So this is essentially that integrated CAM solution that you will have in the product design and manufacturing collections that you would purchase the entire collection. So let's dive into the CAM piece. So what we talk about then, and Al Watmo is our product manager, and he's driving our interface for that integrated CAM, and he has a great video where he outlines his understanding, and he says how we believe in that design and manufacturing should be part of one seamless workflow. So you don't have to have separate tools for your design teams and yourself who's designing products, or an entrepreneur who's making his product or her product. You don't have to have a separate CAD design interface and have a separate CAM. Even 3D printing is another aspect of being able to work and combining the technologies. So you shouldn't have to have multi interfaces to be able to do that. We believe having all that in one seamless workflow is the future here at Autodesk. So these are some examples. Fusion 360 is a standalone cloud solution. Autodesk Inventor HSM, which is our Inventor CAM, integrated CAM directly inside of Inventor. And we also have a solution called HSMWorks, which is an integrated CAM solution that works seamlessly inside of SolidWorks. So let's take a deeper dive into that. What do we mean when we talk about an integrated CAM workflow? So today, in our industry today, often companies will have a separate CAD and a separate CAM interface. You may be working with Inventor or AutoCAD or even SolidWorks, Creo, CATIA, and your design team is working in that environment where it's defined, your design is defined, and that data is then brought into your CAM solution to be able to machine that part, where that whole workflow can be reduced. We can eliminate a lot of that exporting the data and importing it, where you have to reselect your design, you have to reselect all of your components in the standalone CAM system, where we can eliminate that by integrating it directly into one seamless workflow. That's what we mean by integrated CAM. So there's no difference in your interface as you're working on your design than there would be in your CAM workflow as well. So when we talk about that integration, this is our workflow, the simplified workflow of what we do and what it looks like as you're going through the process of adding toolpaths and being able to set it up for machining inside of Inventor. So the first thing you do is you either design or open up your CAD data, your part that you want to make. You just simply bring it into the CAM interface. This is our CAM workflow. If you look at the ribbon bar, the first thing we do is just set it up to match the way we're going to work with it on the machine, define your stock define your orientation, right? And then you pick what operations you're going to do, what makes sense to remove the chips for this part. You're going to do it virtually in the CAM interface, but all the while you're doing this directly inside of Inventor. So you place and you define your operations that you want to do. Then you simulate, you check for any collisions. You can actually see what it's going to look like directly on your part, what that toolpath is going to look like before you move the chips, remove the chips from the model. And then the last step is we are able to export that code. We have post-processor, a very large free post-processor library where we work with machine tool companies. We partner with Haas, we partner with many other machine tool companies to make sure that we have the latest posts that will work in those machines. So we're going to post out the code. It's more or less the interpreter of that generic 2D information of the toolpath and bring it to code that'll run in your machine. And so at that process, you just send it over to your machine and you're able to make that part. And one thing we find, especially in this industry where we have separate CAD and CAM interfaces, is where when you have a design change, and imagine that, a design has to change, happens every day. And so when that design changes in your CAD interface, you don't have to recreate the wheel, pardon me. You don't have to recreate the wheel. You can just go and update your design and it automatically updates all of your toolpaths. Right, so this is 2D, 3D, multi-axis. It'll update those toolpaths directly in your CAD/CAM interface. And this is the huge advantage today, where you have one tool, one interface for your design department all the way through to manufacturing. And that's what we have. This is the simple workflow. We simplified that whole process. These are the 5 tabs that you'll see throughout every toolpath, making it easy to learn and easy to use. So you don't have to hunt around in different boxes to be able to find your different parameters and different aspects of your toolpath. Very simplified overview. So that's the integrated CAM overview. So let's do a little bit deeper dive into some milling toolpaths. And please, as we're going through, and if you guys have any questions, we're going to have a section towards the end that we can have a Q&A session, but please feel free, ask your questions. I believe Kristen and George are going to keep an eye on some of those questions. So if anything pops up, please feel free, ask your questions. This is a live webinar, and we'll do our best to get an answer for you. Okay, so for milling toolpaths, let's take a little bit deeper dive on what that looks like. This is an example of a milling toolpath. This is just an example of a 2.5 axis. So basically, we position the part or the tool in Z, and then the tool will stay at Z, and we do our X and Y chip removal throughout the part. That's what we have available for 2.5 axis toolpaths. These are some of the milling strategies. And you see the standard, excuse me, you see standard toolpaths that you find throughout the interface, where you do pocketing, do facing, 2D contouring. And we do have
Wayne, I'm going to interrupt you for just
Sure.
one moment. It looks like we're having a problem sharing your screen. We see the M2 technology slide, but we're not seeing anything progress.
Oh, I apologize. Okay, let me go back. Here we go. I apologize for that. Looks
Excellent.
like it
Thank
was
you.
paused. Absolutely. So as I was going through, I apologize you weren't able to see as I went through this workflow. I'm just going to kind of go back real quick so you can have a good idea of the things that I was overviewing. So why integrated CAM? And this is the screen I had up, and I apologize that you weren't able to see it. But this is the screen I had up that we were defining the separate CAD and CAM interface. All those steps, we just simply will be able to eliminate most of the export and import steps where we find a lot of problems with standalone CAD and standalone CAM, and where we integrate it. And this is the slide I was just showing. So when we integrate those, we can integrate them into one workflow inside of one integrated CAM and CAD interface. And so we're simplifying that process. This is where I was walking, where we create our design, or we open up our design. We define our setup to match the way we're going to machine the part. We have our stock boundary as well as our orientation. And the next step would be simply applying your operations, applying the way that you're going to remove the chips. And then we simulate the check, and this way you can see what the toolpath is going to look like if you have any collisions that you can avoid. And that final process is outputting your code. That's it, the simple workflow. for defining your part or defining your CAM and being able to do it all in one workflow. And design changes, as I had mentioned, design changes will happen. You can see you can update your design directly inside of Inventor, and it'll update all of your toolpaths automatically. And that's the power of having integrated CAD CAM in one solution, in one tool. And as I'd mentioned, this is the workflow. This is the 5 steps that you would find throughout all of the toolpaths. Right, so this is what's going to make it really easy to learn and easy to use. And now we're up to our deep dive into milling toolpaths. So again, I want to show you this example of a simple 2.5 axis milling toolpath where we position. This is a piece operation, and then we're going to see a contour or adaptive clearing roughing here, where we position the part in Z, and we do our XY cutting, and then we reposition the part in Z. So those are our 2.5 axis toolpaths. These are our 2D milling strategies that require 2D geometry to drive them, like lines, splines, arcs, and points. And also included is our 2D adaptive clearing. There's our high efficiency machining, adaptive clearing, where we go deep on the tool and we keep a constant load on the tool, always the same chip load. And this is part of the 2.5 axis, as well as it's the part of the 2D milling strategies, but it comes automatically as part of your subscription. So there's nothing special you have to get to be able to do high efficiency machining. And some other examples of 2D milling strategies where we can do some threading, even tapered threads, slots, and 2D chamfers as well. And our engraving tools and other toolpaths like drilling, of course, and trace toolpaths. Okay, so just give you an overview of what some of those toolpaths look like. You might see some familiar shapes, some familiar toolpaths that might look like it would work on your parts. And so these are just some good examples of what those toolpaths would look like on a part, to give you an idea. 3D, or shall I say 3-axis milling, this is where we actually move in Z. So as the tool is working around cutting the chips, it's actually ramping up in this case in Z. So we do have constant X, Y, Z motion. Therefore, we have our 3-axis simultaneous toolpaths. And these are some of the examples of those 3D milling strategies. And again, we have a 3D adaptive clearing. So we take that same deep engagement, the constant radial engagement, and we work up the walls of the part, almost like we're cutting it out like a pyramid so we can come back and finish and not have to cut through all that raw stock. So you have that high-speed machining, that high-efficiency 3D toolpath adaptive clearing that comes part of our interface. So we'll talk a bit more about 3D adaptive clearing soon. All right, so we have our parallel, which is similar to your waterline toolpaths and other interfaces, ramp and contour toolpaths. And then our 3D strategies for horizontal, pencil, which don't really need any boundary. So they look at automatically the places where you have horizontal faces and transitions between walls that have to be machined. The toolpath will automatically recognize those areas. Spiral toolpath, scallop toolpath, very effective for when you're doing mold making. And other toolpaths where we have strategies for specific types of parts and specific interfaces, like radial toolpaths, a morph spiral, which will then take like a circular spiral and work its way out to match the shape and contours of the part. Project toolpath, so you can have your design in your sketch, and you can simply put a toolpath which will project it down to a surface. Morph toolpath, which will change its shape and change its step over according to the boundaries of the design that you're working on. So these are some of the other solutions, and this is how they would look like on some of the parts that may match the parts that you guys are working on. So you can see a combination where we do a contour and ramp in the center there, and then follow up the top with a scallop. Often we would see where a combination of different solutions might give you the best finish and give you the best approach when removing those chips to get the part that you want in the end with your tolerance. So just to give you an idea of what some of the 3D finishing strategies look like. Okay. So we're able to dive in a little bit in what we offer as far as milling toolpaths, 2D toolpaths, 3D toolpaths. And what I'd like to do is I want to get a little bit deeper in adaptive clearing to talk about what that high efficiency machining looks like. And so adaptive clearing, where we have traditional roughing on the left. So traditional roughing is basically offset pocketing. So we take the shape that we want to be able to pocket, and this would actually just simply do an offset of a step over a size that you would determine and a minimum size, and the tool will approach those areas, but always keeping a constant offset distance, right? So it's, you'd have to, especially in toolpaths like this, where you got to slow down in those corners because you're going to get over, you're going to overwork your tool, overload it, and bury in the corner. Where adaptive clearing, the difference where we have high efficiency roughing is always keeping that same chip load on the part. So as you work through the material, you're always keeping the same chip. And in a place in a corner like this where it's not able to keep that same load, we'll lift off, we'll do what we call as a micro lift. We're going to wrap it over and it's going to feed in at another bite at the same exact chip load. It'll continue that all the way through down into the corner where you're always keeping the same load on the tool, especially when you get into the corner where you're not going to overload it, bury your tool. And often in a traditional sense, we'd bury the tool in the corner, we'd have to slow down our feed rate a lot. So with a high-speed adaptive clearing, you can run your spindle speed a lot quicker, and you can reduce that friction between the cutting edge and the material and pull all that heat out with the chip. And as you're doing that, you're always keeping the same constant load, so you're going to eliminate burial, you're going to save tool life. You get your parts off your machine a lot quicker, and you're going to save tool life. And that's what we mean by high efficiency roughing. Right, so here's some examples of what they look like. As you can imagine, as that tool gets closer to some of those corners, I'm just going to kind of drag us a little bit quicker. But you see when it gets into some of these corners down here, especially there, right in that one section right there, that's exactly where it's going to end up burying the tool. Where we have adaptive clearing, and if you watch as it approaches, you can see we're always keeping that same load on the tool the entire time. Right, so you get more efficient tool path, especially here in the corner. Right, it's going to back around, come back around, it's going to back its way and keep that constant bite as it works into the corner. You won't get that burial, and you don't have to slow your feed rates down because it's always constantly updating the tool path according to the material that's left. So that's an example of what the differences are between traditional tool paths and high-speed roughing. Just another example just to show you that engagement angle, right? So in traditional, you can be engaged, let's say, a little over 40, almost 45 degrees on your cutter. And when you get into a corner, you can almost be at 180, and especially up here, you're more than 180 engaged. And that's actually going to bury the tool. You got too much chip filling up your lead angle, or so I say your tooth, and filling up and pulling those chips out, where adaptive clearing, we always keep that constant engagement angle. So just another view to get a better understanding of how a high efficiency roughing, especially adaptive clearing, are being used in our software. Just a little bit of another point where traditional roughing often will run very shallow on the tool, because if we go really deep with like offset cutting and traditional, we will find that you'll break the tool or you'll overload it really quickly. So often people will avoid the depth, the axial depth, by keeping the tool very shallow the entire time, and also see those load spikes in internal corners where you slow your feed rate down a lot. So in high efficiency machining, we can go as deep as possible. I mean, you have all that flute length, you paid for all that tool, you might as well use it all, right? And you can keep that constant radial engagement full through the depth of cut the entire time. And all of that radial engagement's being controlled by our chip load, right? So it's always the same size chip being pulled out, and that's why you can run higher speeds and you can go deeper in the material. So that's an overview of our high efficiency machining, which is our adaptive clearing. So what I'd like to do is get a little bit more into turning toolpaths. So we do offer a solution for your turn machines, and we'll take a look a little bit too on mill turn. It's just basically looking at working with our 2D turning toolpaths and mixing them with the 3D or 2D milling toolpath, and then the post will output the correct code to give you your mill turn solution if you have a C-axis or Y-axis. And we'll dive into that a little bit too. So for traditional turning, in this case, we have turning toolpaths. And so as we know, some people who are working in the milling world would like to learn a little bit more about turning, where the part itself is in a chuck, or shall I say in a spindle, and the part is spun, and you have an axial distance from the center out, and we have a tool, which we would sometimes call a static tool, but we have a radial tool or an axial tool that moves on a turret, that large tool holder up there, and it'll move throughout the material as the tool turns. We're removing the chips from the rotating part. And so in our turning solutions, we have a face toolpath, we have turning profile, and turning groove. And what's really neat is it's exactly the same workflow that you would have on the milling side. So the same exact steps you would take to set up your part, to apply your toolpath, and a lot of the toolpaths will recognize the geometry that you're selecting, or you don't have to select it just inside of a boundary. We have those solutions that we can apply directly to the part. So chamfering, threading, turning and parting the part off. And to give you an example of what some of those toolpaths would look like on a part. So we have grooving, single grooving, chamfer toolpaths. The profile, again, we can set it up to match the actual profile of the part. And if you're doing mill turn, we can do a spun profile to be able to make sure that you're cutting the part to its silhouette. So we have those turning solutions. For mill turn, we do have a solution for mill turn where we apply simply those radial engagement toolpaths. In this case, we're going deep with the side of the tool, and we're able to do that pocket and that groove out on the Y-axis of this machine. So it's simply just applying one of the 3D or 2D strategies to your Y-axis or your C-axis, and it'll actually give you the code for your machine to be able to do the live tooling operation. Okay, so for multi-axis toolpaths, we do have a solution of multi-axis. We have some that are simultaneous multi-axis toolpaths, and we have ones that are positional or indexing. In this example, this is indexing, where we have a 3+1. Simply means we're going to rotate around one axis, like the A axis, bring the part into position, and then we will do a 3D or 3-axis toolpath, or even a 2.5-axis toolpath on that part. So we basically position it for machining, and then reposition it for the next operation. And that's what we mean by 3+1. We do have solutions, and every one of our 2.5-axis and 3-axis toolpaths can do positional. So we have a function inside the toolpath where you can do tool orientation, enable it, and then you can orient the part however you need in your rotary axis setup. So we do have a solution for 3+1. This is an example of a 3+2. We did this on a Haas UMC 750. This is one that one of our application engineers at Pier 9, CJ Abraham, set this part up, and he was able to demonstrate really well how we do 3+2. There's a great video on YouTube if you'd like to walk through exactly where this came from. But so this is 3+2. So we move in 2-axis simultaneous, but we lock, and then we come in to do a 3-axis or 2.5-axis toolpath. So that is what we mean by 3+2 positioning and 3+2 milling. And again, so we do have all of our 2-axis and 3-axis and even our 5-axis simultaneous toolpaths that we can apply positioning to in your A and B or your B and C axis tool or machine. Okay, just give you an idea of what some of those multi-axis strategies look like. So a swarf toolpath is going to use the side of the tool. I like to say it basically rolls around your part on rails. So you can select faces, you can select edges and contours, and the side of the tool will remain normal to those contours or those faces that you select. This is a simultaneous fifth axis strategy. The same thing with the multi-axis contour. So in this case, we use the tip of the tool, and that tip of the tool will stay normal to the surfaces of the model, will respect those surfaces, and it will follow the geometry that you select or create on those surfaces. So that's our multi-axis contour, a constant fifth axis strategy. And we also have, then this is another view of some of the other strategies. We have tilting. So this is actually applying control of the tool itself, the shaft of the self, and the holder, where you can set up a clearance and you can apply a multi-axis solution to a 3D toolpath. So in this case, it looks like we're going around doing a pencil toolpath, or we actually have a constant three-axis contour where you can apply a fifth axis solution. So it's essentially going to tilt the tool to avoid any collision of the part, but it's going to follow that geometry to cut along that face. So we do have toolpaths where you can apply fifth axis strategies to a 3D type toolpath, like a multi-axis flow. This is where you can apply a toolpath that's going to follow the UV normals of the surfaces that you're selecting, and the tool will follow that around the ball edge, and the tool will keep itself normal as many step overs as you need with those surfaces. So it's another example of a flow toolpath that can be 3-axis, 4-axis, or 5-axis solution. So we do have toolpaths where you can apply simultaneous multi-axis to 3D solutions. Okay. And here's an example of a 5-axis router. This one we did a couple swars, we did some positional, but this is an example of the multi-axis contour using a head-to-head machine at Pier 9. So this is the DMS router, and it's working around that Iron Man mask. And that's just an example of that solution keeping the tooltip normal to the surface as it follows the contour of the mask. Okay, so that's been our overview. I know I went through the beginning. I apologize for doing a lot of talking and not showing you the slides, but hopefully my going back kind of gave you a better idea, an overview of what those toolpaths look like, what the solutions are inside of HSM, which is our integrated CAM solution for Inventor SolidWorks. And we have it in Fusion 360, which is our single cloud solution. And it's not only, and this is also what comes inside of our product design and manufacturing collection, and these are part of the manufacturing solutions at Autodesk. So I just want to go back to some of those slides we saw at our initial preview or initial overview, where this gives you some of the benefits of what our HSM offers that you would have to apply to your strategies in your work. So reducing cost. So it's definitely worthwhile just to have the adaptive clearing, reduce time, improve your productivity with all of our toolpaths, and having it all inside of one integrated solution, right? So you have advanced features, you have ease of use. The 5 tabs that I showed you is basically all you need to know to be able to apply all of the toolpath solutions. Easy to learn and easy to use. Okay, so these are some of the capabilities and some of the benefits of working in HSM, as well as Fusion 360, which is also part of our product design and manufacturing collection. Fusion is really looking at the future of Autodesk. It's really one solution that you can do generative design. This is newly added to our solutions as far as Fusion is concerned, where you can have ideas, you can have your design input. You can have your design requirements where you can load those into a cloud solution where an AI will help you with your design. We'll take a look at some of those places where you wouldn't think about lightweighting or increasing your factor of safety to apply to your design, and you'd be able to manufacture it using some solutions for milling and fifth axis machining, as well as metal printing and 3D printing and additive technologies. And so it opens up a lot of your design avenue that you wouldn't normally have today in today's design world. So you have generative design as part of it, being able to do full simulation, which is Nastran in CAD, which also comes in our manufacturing collection as well, or design and manufacturing collection. But it's essentially Nastran that runs inside of Fusion 360 to help you do simulation tests. You know, your stress strain analysis. You know, doing thermal buckling, that nonlinear stress as well. And of course, the same integrated HSM CAM is inside of Fusion 360 as well. And so, and then we also have our cloud collaboration tools as other benefits to help you get stronger, faster to market, and being able to make things that you didn't think were possible. So that's all part of our manufacturing solutions. If you're working in Inventor, we have that Inventor CAM, which is HSM directly integrated inside of Inventor, and those are our solutions that we have for CAM. So with that, I know we're quite early. This was a good half hour spent. Hopefully, I was able to help with some of your questions, or at least help answer some of them ahead of time. I'd like to know and ask Kristen and George if there's any questions from our audience, and this would be a great time to get some answers.
So Wayne, there is one question pending, and the question is, are you generating toolpaths? Sorry, are you generating toolpaths only, or are you generating the complete code to run on specific hardware?
So we are actually doing the entire gamut. So we're generating the toolpath, the path of course your machine would follow, and then the last part of that is to post-process the code specifically for your machine. So if you run a Mazak machine or a Haas machine or Kuma, and you have a CNC machine control, what we're doing is we have post-processes that will take those generic toolpaths that we generated. It will if you think of a post processor like a decoder ring, it will then take that generic process, it will code it into the language that your particular machine understands, and you can bring that code directly to your machine, so it will mimic exactly what you did inside the 3D CAD CAM interface. So to answer your question, we go all the way through to be able to run on your specific hardware. Okay, so any other questions we might have?
Got one more.
Okay.
So for 3D printing, code to generate support is included?
So there are a few different solutions when we talk about additive and subtractive manufacturing. So when we talk about CAM, we're really focused on the subtractive part, where we remove chips from a block of material. When we talk about additive and 3D printing, and 3D printing isn't only plastics, it's also metals, where we do additive, and there are solutions, there are an interface, especially with Fusion that's coming soon, the ability that you can actually have a metal deposition head on a machine that you can actually print out on a part that you're going to machine at the same time. So with that said, the approach that we have is a few different ways that you can make a part. So if you actually design a part in Inventor, or you design a part in Fusion 360, and that part is your purpose is to 3D print it, we do have a direct solution that can output the information needed for a 3D printer, like a SourceForge or a MakerBot, that can 3D print your part directly inside of the interface. So that isn't really a code generating software. You don't have to put toolpaths. What we do is we call a slicer, where you'll have an interface for a slicer where it'll lay down material layer by layer. And you can see that, and you can work with the layer thickness. You can work with the how many layers you need to be able to make the part if you need support material. So we do have interfaces specifically for the 3D printing industry, but to expand on that, we also have additive and subtractive solutions where we can generate the code for the larger industrial machines to remove chips as well as add and deposit material on the part. So I know that was a very larger explanation, but to answer your question, yes, we can generate the information needed for and the code, as well as the parameters needed to be able to 3D print a part, as well as being able to remove the chips and be able to do additive manufacturing. Okay,
Wayne, I believe that was the last question.
okay. Oh, you guys are taking it easy on me today. But I'm happy. So if you guys have any questions following this webinar, please feel free to reach out to the team at M2 Technologies. And they have some really good engineers there and support. And so please reach out to them and they'll get answers. And if there's some that are specific to this webinar, they can definitely get in touch with me and I can always provide answers as needed. And we also have a team here at Autodesk. So if I'm not going to be able to provide an answer, I can get one from some of our experts here on our team. So yeah, please feel free, reach out, M2 Technologies. These guys are here for you and to answer your questions and help you guys get some great products made and manufactured. Awesome. I think with that, I think that's all I wanted to show today.
Wayne, thank you so much. Everybody, thank you for attending. We look forward to seeing you on the next presentation.
Yep. Thank you, everybody.